know that you can consume vinegar which contains citric acid, but you cannot consume sulfuric acid which is used in the manufacture of most fertilizers, batteries, etc. A base like baking soda is used as one of the ingredients in making cakes and its edibles. Whereas you need to be very cautious while handling a base like drain cleaner. Can you think why is it so? The answer lies in the ability of each acid or base to break apart or dissociate. Strong acids and bases completely dissociate into their constituent ions in an aqueous medium. Strong acids donate H+ ion in their aqueous medium. Consider a strong acid Ha. It will dissociate into H+ and A- ions. Similarly, strong bases completely dissociate in their aqueous medium and give hydroxyl ion, that is OH-. If MOH is a strong base, it will give OH- and M+ ions. Since the dissociation is approximately 100%, these are irreversible reactions. Some examples of strong acids are perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid. Can you think how hydrochloric acid will dissociate in its aqueous medium? You know that hydrochloric acid is a strong acid, so it will dissociate into H+ and Cl- ions. Here, H+ ions combine with water molecules to form H3O+ ions, that is hydronium ions. There are no HCl molecules found because 100% of the HCl molecules break apart into hydrogen ions and chloride ions. As a strong acid dissociates completely in water, the resulting base formed would be very weak, that is, strong acids have very weak conjugate bases. Some examples are perchloric acid is a strong acid and its conjugate base is chlorate ion ClO4- is a very weak base. Similarly, strong acids like hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid will give conjugate base ions Cl-, Br-, I-, NO3- and HSO4- which are much weaker bases than H2O. Some examples of strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide and barium hydroxide. Now, let us talk about weak acids and weak bases. Weak acids and bases partially dissociate into their constituent ions in their aqueous medium. Let us take an example of hydrofluoric acid, which is a weak acid. If you zoom in, what will you find at the molecular level? We will find that only few HF molecules have dissociated into hydrogen ion and fluoride ion. So basically, in weak acids and bases, equilibrium exists between ions and unionized molecules. So, weak acid partially dissociates and at equilibrium, both the acid and its conjugate base is present. Consider the acid-base dissociation equilibrium of a weak acid, say Ha, where Ha is an acid and A- is its conjugate base. Some examples of weak acids are acetic acid, hydrofluoric acid, nitrous acid and formic acid. Weak acids have very strong conjugate base. Typical weak acids like acetic acid, hydrofluoric acid, nitrous acid have very strong conjugate base CH3COO-, F- and NO2- respectively. Similarly, weak base partially dissociates and at equilibrium both the base and its conjugate acid are present. Consider the acid-base dissociation equilibrium of a weak base MOH, where MOH is a weak base and M plus is its conjugate acid. Now, the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? What is the driving force behind it? In order to answer these questions, we will look into the issue of comparing the strengths of two acids involved in the dissociation equilibrium. Again, consider the equilibrium reaction of a weak acid HA. There are two acids here, HA and H3O plus. Now, you have to check which acid is a stronger proton donor. Hope you remember that in our last video, we learnt about Brondted-Lowry concept of acids and bases. Whichever acid will have more tendency to donate proton will be stronger acid and the equilibrium will shift towards the weaker acid. Let us say HA is a strong acid than H3O plus, then the equilibrium will shift in the direction of weaker acid. Then HA will donate protons and not H3O plus, and the solution will mainly contain A minus and H3O plus ions. We can say that equilibrium will shift in the direction of weaker acid, that is H3O plus. Do you remember that we discussed in our previous video that water can act as an acid as well as base? It is one of the very unique properties of water. So, does water also ionize? Think. Water can act as an acid as well as base. In the presence of an acid, it acts like a base and accepts a proton, while in the presence of a base, it acts like an acid and will donate a proton. Let us understand this by considering two water molecules. One water molecule will behave as an acid, that is, it will release H plus ion and will form OH minus ion, and the other water molecule will behave as a base, that is, it will accept one H plus ion and will form H3O plus ion. Mathematically, dissociation constant is given as concentration of H3O plus multiplied by the concentration of OH minus divided by the concentration of H2O. Since water is a pure liquid, its concentration remains constant, so its concentration is omitted from the denominator. Concentration of water is incorporated in the dissociation constant K, so we get a new constant Kw, which is the ionic product of water. Can you suggest how to calculate the value of Kw? Experimentally, the value of the concentration of OH minus and H3O plus at 298 Kelvin has been found to be 1 into 10 raised to the power of minus 7 molar. Placing both the values, we will get the value of Kw as 1 into 10 raised to the power of minus 14 molar square. Please note that the value of Kw is temperature dependent, which means if the temperature changes, the value of Kw will also change. Now, imagine your teacher gives you a solution and asks you whether the given solution is acidic, basic or neutral by relative values of H3O plus and OH minus concentrations. Can you guess? How will you find that? It depends on whether the concentration of OH minus or the concentration of H3O plus ion is more. If the concentration of H3O plus ion is equal to the concentration of OH minus ion, then the solution will be neutral. If the concentration of H3O plus ion or H plus ion is less than the concentration of OH minus ion, then the solution will be basic. This will be discussed in detail in our next class. Now, let us summarize what we have learnt.
Manorama Horizon. Learning made simple.